Okay, so interlacing property. This is a beautiful property that is so easy to describe, but it just somehow rarely to be taught in undergraduate courses. And I don't really know the reason. It is not particularly hard to prove that. But let's first to look at the description, the statement of this property. Okay, so suppose we have a matrix A which is m by n, and it is symmetric. So we can imagine that A is a matrix and it looks like this. And if we have a m by n matrix, then we can pick its m minus 1 by m minus 1 submatrix, that is a principal submatrix. Okay, so let's say B is an m minus 1 by m minus 1 principal submatrix. So in fact, it can be here. It can also be the top left. It can just be something that we remove one column and one row of the same index. Now, that's all the setting. And we cares about the eigenvalues of A. And so we say lambda 1 to lambda n are the eigenvalues of A, and for B it is m minus 1 by m minus 1, so we say the eigenvalues are mu1 to mu m minus 1. And meanwhile, we want to order them from small to large. So the interlacing property is the following. It is actually a theorem. You can call that interlacing theorem. So following the same setting, and we have lambda 1 less than or equal to lambda 2, and less than or equal to something else, and keep going up to lambda n. And this is known just because we order them from small to large. But meanwhile, we also have the mu1, which is less than or equal to mu2, and which is less than or equal to mu n minus 1. And the interlacing property says that actually not just these two inequalities, these two sequences of inequalities, actually we have these properties, which means mu1 is greater than or equal to lambda 1, and then mu2 is greater than or equal to lambda 2, and keep going. And so you will see that lambda 2 just fall in between mu1 is in between lambda 1 and lambda 2. Mu2 is in between lambda 2 and lambda 3. And that's why we call that as interlacing. Interlacing is like a 交错. So you see, this is a property that can be easily described, and it's so elegant. If you pick the matrix A and then pick one of the principal submatrix of order m minus 1, then their eigenvalues will have this kind of interlacing property, and it just alternating between lambda and mu's. So more generally, we can talk about A and B of different sizes. B is not necessarily a matrix of m minus 1, of order m minus 1. So in general, if B is a K by K principal submatrix of A with eigenvalues mu1 up to mu k. And again, we order the mu's from small to large. And because it has order k, so there are only k eigenvalues here. Then, in this case, we are able to say that mu I is greater than or equal to lambda I and less than or equal to lambda of m minus k minus I. And I will explain how to remember these indices. But that's all the statement. So let's try to understand this part. Okay, so here is how to remember that or visualize the idea of this inequality. So imagine that we got lambda 1 and lambda n, put that on the real line. And so we got lambda 1 and lambda 2 and then keep going on because it is ranged from small to large. And what we have seen before is that there are some eigenvalues between lambda 1 and lambda 2 and lambda 3, and keep going until lambda n minus 1 and lambda n. So if you just take out one column and one row, the eigenvalues of the principal submatrix will be here. But somehow we take we take out too many rows and columns. So how it looks like is something like this shape. Okay, and we got mu1 and mu k because we dropped too many layers. M minus k rows and columns. So because we take out too many rows and columns, now we only have k eigenvalues. And in order to remember that, one easy thing is that mu1 is still greater than or equal to lambda 1, and mu k is still less than or equal to lambda n. The smallest is in between the small and the biggest, and the biggest is still in between the small and the biggest. But how about something in the middle? If I pick this one, this is mu I, which is this one, okay? I take a particular mu I, and what I can see is, let me move it to the right a little bit. What I can see is try to make the same shape and move that to the top. So it will move to the top left, top left, top left, top left, and then reach to this eigenvalue. And it is not hard to see that because here is 1 and I, then here is 1 and I. So the top one is lambda I. So we got the inequality mu I is greater than or equal to lambda I. Well, this is not a proof. I'm just saying that you should think of that in this way. And on the other side, you can go to the top right, top right, top right, and reach to another eigenvalue. And now you need to calculate what it is, because the difference between I and k is k minus I, right? So the difference between n and this one is also k minus I. So try to remember that as lambda n, and then counting from the right and to the left, minus k minus I. Okay, so that's how we get the inequality. Mu I is less than or equal to lambda m minus k minus I. So although the subscript looks quite long, it has 3 letters, but still it's just an idea saying you should go to the right hand side, and that's the biggest thing that you can do. So let's really show you an example of how it works, and in particular this is kind of the ideal picture that we are using, because in many cases maybe lambda 2 has a multiplicity 3, so maybe lambda 2, lambda 3, lambda 4 all equal to this same quantity. So in that case you have to imagine, put some imagination to visualize this work. Okay, so in order to do that, let's look at a concrete example. This is the adjacency matrix of K23. We call that A, and it is lots of zeros, okay, so a fact about this kind of matrix is the following. We will go through that in the future, but let's just try to use this fact to see the interlacing property. The spectrum of this guy, OM, and the JMN, JNM, this means here has M columns, here has N columns. The spectrum of this matrix is equal to lots of zeros and square root of M times N. In fact, it is plus and minus, but let's put the minus in the front because the order. And so this is the fact about this kind of matrix. One side is, part of that is quite easy. You just look at the nullity of this matrix. You see this matrix has a lot of rows in common. If you look at all the rows, it has M rows that are all the same. It has N rows that are all the same. And there are only 2 different rows in this matrix. So we will know that the nullity is equal to M plus M minus 2, and the other 2 is coming from here. If you want to know the last 2 eigenvalues, then you can calculate the trace. The trace is equal to 0, so the eigenvalues has a sum equal to 0. You can also calculate the trace of A squared. Then you can get M times N. But just forget about that at this point. Let's look at a concrete example. Okay, so let's call this as A. And we'll try to find some submatrix of that. So let's call this as A1 and call this as A2. So you see that A1, let's call A itself, the spectrum of A following the fact is equal to 3 zeros and root of 6, 2 times 3. Okay, and so the next one, spectrum of A1, it is the adjacency matrix of K1 3, right? 1 and 3. So the eigenvalues are square root of 3 plus or minus of that, and 0, 0. And the last one is all zeros, and I believe we all know the spectrum of that is equal to all zeros. So as you can see, it does has the interlacing property that the first eigenvalues of A1 is in between minus root 6 and 0. And the other thing is the same. If you have two zeros going together, and then there will be a eigenvalue in the next one. So see, for example here, the multiplicity is equal to 3, then the multiplicity of the next one is at least 2. At least 2. It can be 3, it can also be 2, it can also be 4. So for example, if you see here, if the multiplicity is equal to 2, then it is possible to get multiplicity equal to 3 again. It can drop or increase, or it can stay the same. But as long as it satisfies the interlacing property, it is possible. Okay, and when you calculate the middle one, for example, this one is greater than or equal to this one, greater than or equal to this one, and this one is greater than or equal, less than or equal to this one, this one. So if you know the spectrum of the top one, then you already know that this is always going to be 0. This is like a triangle that we have 3 zeros, 2 zeros are guaranteed, 1 zeros are guaranteed. And but starting from here, you know the next 2 is going to be 0, 0, and next 1 is going to be 0, right? So that's the idea of interlacing property. It is just an elegant statement that is so easy to describe and easy to remember. Okay, so there are some questions or problems in your handout, and you can give it a try now, or here is another, if you want to do some more exercise, or just try to think of that in your mind. Okay, J4 is equal to the O1's matrix. Four by 4, and try to think about what is its spectrum. And then J4 will drop down to J3, drop down to J2, and try to make also the same picture like this. So you can try to make the same thing like this, and try to observe how many zeros and what are the eigenvalues of that. This one is not on the handout, but you can either work on the handout or try to work on this one. But that's the lecture for this hour.